Hell, this is Nature 1000, and today we are going to finally do duodecimal division, or base 12 division in ancient binary. And I'll try to translate it as best as I can. Let's see, I did a few takes of this and I screwed up. And basically by the time I uploaded the video already, like I realized that, oh my gosh, I made these few mistakes like along the process, and so then I took a break to think about it. But I already did discover a bunch of stuff of like how to do it on the first takes I took. But now I understand it after my mind is cleared and everything. So let's try to translate this as best as we can. So we will start off with, we'll try to convert 13 divided by 690 in ancient binary. And so the first step, we start off with one set of 12, and then plus 1, so that's 13. So now we have the first side done. And then now we have to convert 690 into ancient binary. The third placeholder, for division, it's very important to know the placeholder is when you have a base. That's basically that's the basic concept that I discovered after experimenting with this. So basically 144 is the third placeholder, and so how many 144s goes into 690? Basically times 4. So 16 put the 1, 17 put the 1, so now we have 576. We put the 4 here. And by the way, on this side we're just going to put a 4 because we're just going to do a step-by-step process. 4 sets of 144. So now, after that, we go to 690 minus 576. Cross that off. 414. So now we have 114 left over. So now we need to go to the next placeholder, which is 12s. How many 12s goes into 114? And so if we divide 114 divided by 12, that gives you 9. We'll just put that symbol there. And 9 sets of 12 equals 108. And then basically now we subtract 114 from 108 to see our ones placeholder. Borrow that. 14, 13, 12, 11, 10, 9, 8, 7, 6. So we have 6 left over. So our final number for the conversion process is 6. And so now this is 690 in ancient binary, base 12 basically. The next thing we need to do is we need to think of this 0 13s goes into 4. So basically we move on to the next placeholder, which is 9. And now we need to think of this placeholder as the 12's place and this as the 9's place. So we're going to move down now. So now we have 4 times 12. This is 48. And then we have plus 9. 16, 17, put the 1. Now we have 57. So now we need to figure out how many 13s goes into 57. So 57 divided by 13, okay, equals 4. So now we would put 4 up here. And so now we need to multiply 13 times 4. There's a step-by-step process here. 12, put the 1. So now we get 52. So now we need to convert 52 into base 12. Because we keep going back and forth. 13. So 52 divided by 12 equals 4. And so now we subtract. To get our ones place, we have to subtract 52 from 48. We have 4 left over. So basically, this is our ones place. This is our 12s place. So now we go back to up here, and we subtract this. We use the down symbol for subtraction. And so now this equals 0, and then this equals 5. We now have the 56. So now our next step is to figure out how many 13s goes into 12 times 5 plus 6. 12 times 5. So there we go, now we have 66. So that number equals, or this number is converted to 66 in base 10. The next step is we need to do 66 divided by 13 equals 5. And if you multiply this, that equals 65. Your next number would be 5. 5 is up here, and then next we have a point, which is basically a comma. It's like reverse in ancient binary. We need to convert 65 into base 12 again. 65 divided by 12 equals 5. And because 5 times 12 equals 60. So now we subtract this, and we have 5 in the ones holder, and we have 5 in the 12's place. So now we move up, and we'll once again subtract. Once again, we'll subtract this. And so now this equals 0, and 6 minus 5 equals 1 left over. The next step is we have to move to the decimal points, and the decimal points in ancient binaries are commas. It's reverse, like if there's an extended high number, it's like periods, but if it's like a decimal point, it's a comma in ancient binary. It's reverse. Okay, so the next step, we have 1 left over. After this, we have 1 left over, and we have to add this 0. And 13 goes into 12 0 times. So unfortunately, we have to add another 0 right here to equal 144. 13 goes into 143 11 times. And then we get this symbol here, because this is 6 plus 5 equals 11. That's where you get 11 in ancient binary. 13 times 11 equals 143. And so now we have to subtract 143, or from 144. We need to do some carrying over. And by the way, since 13 goes into 144 11 times, we put the 11 up here. So now we have 45.0L in the duodecimal terms. And so basically we cross this off to equal 0, and then we have to cross this one off because basically 12 gets carried over here, so we have to put 11. So now this is 11 minus 11 equals 0. and then we carry the 1, so this would now be a 12. 12 minus 11 equals 1. This would keep repeating, 0.0L, 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 because it would keep equaling 143 over and over again, minus 144, as you just kept going on. So the final answer is 45.0L.